Hello everyone. In this lecture we shall discuss the cutting plane technique to solve the integer programming problem. Okay. We will discuss the cutting plane algorithm, cutting plane technique to solve the integer programming problem. In the previous lecture we have discussed the branch and bound technique. So basically the cutting plane algorithm starts at a continuous linear programming solution. That solution is by the simplex method. We solve the problem first by the simplex method. Okay. Special constraints called the cuts are added to the solution space in a manner that renders the optimum integral extreme point, and that can be done by using the dual simplex method. As I have told you earlier, suppose 5.7 number of persons to be hired for a work, then it is a vague thing, impossible thing. 3.9 number of machines to be installed in a workshop, this is also a vague or absurd thing. So to deal with this such case, we have two techniques. One is the branch and bound technique, other one is the cutting plane technique. So now this cutting plane technique, as we have seen, first we have to solve the problem by simplex method. We have to understand the solution space. If the solution space is not integral, we develop a cut to squeeze a little the solution space to restore the optimality, and that can be done by using the cut. As we are using both simplex method as well as the dual simplex method during the process of the solutions. So let me to explain the working rule for the simplex method as well as the working rule for the dual simplex method. So coming to the simplex method, first we bring the problem in standard form. Okay, bring the problem in standard form. Ensure the right hand side of the constants are all non-negative. Okay, greater than is equal to 0. Bi greater than is equal to 0 for all I. Then we select an entering variable. We select an entering variable by using optimality condition. By using optimality condition. Right? By using optimality condition. So here the optimality condition means we have to see whether this del j net evaluation is greater than equal to 0 or not. If yes, then optimality achieved. Optimality achieved. Okay. So thus the non-basic variable, that means we have to first select the entering variable, which variable is entered into the base. So the non-basic variable having most negative del j net evaluation, most negative del j in maximization problem, in minimization problem, in max problem, and for mean problem we have most positive del j. Okay, so basically let me talk about the max problem, because we can bring the mean problem to max. As minimization of minus z is minus max minus z. Okay, in that way this minimization can be converted to maximization. So I am explaining it for the maximization. Okay, most negative. So the non-basic variable having most negative will enter into the base. Right? Will enter into the base. This is your optimality condition. Then after one variable will leave into the base, another variable needs to be leave from the base. So we have to find a leaving variable. Okay, that leaving variable is based on the feasibility condition. What is that feasibility condition? This feasibility conditions means one basic variable will leave from the base. That basic variable which will leave from the base is subjected to the minimum ratio of your solution column. Okay, solution column to the entering column, and here the denominator should be strictly positive. Okay, strictly strictly positive denominator. Okay, those denominators which are negative will not take part. So in that way we will find the minimum ratio, and this variable will enter into the base. And after this variable will enter into the base, we have again a new set of the basic variables. So now this new set of basic variables to be restored under the identity matrix by using Gauss-Jordan elimination. Okay, and we continue the process, okay, of entering and leaving. Here first is entering and second is the leaving, right? Continue this entering and leaving until we achieve that net evaluation del j is greater than equal to 0. So if I explain one example, then your idea will clear. Okay, then coming to the dual simplex method, the working rule. So let me to introduce myself. Professor S.K. Paikray, currently working as a professor of mathematics at Veer Surendra University of Technology, Burla, Odisha, India. Okay, so now let me to explain the working rule for the dual simplex method. So in dual simplex method, we have to first bring the problem into canonical form. In simplex method, we bring it in standard form, in canonical form, by ensuring the right hand side of the constants is less than equal to 0. But here the right hand side is greater than equal to 0. So now once the right hand side is less than equal to 0, means the feasibility is hampered because solution is negative. We have the linear programming problem. We have the non-negativity restrictions, but the non-negativity restrictions here is hampered, right? So the feasibility is hampered. So first we have to select the leaving variable here. So in dual simplex method, we have to select the leaving variable. In contrast to the simplex, in simplex we first select the entering, but here we select the leaving with variable by using the feasibility conditions. So what is that feasibility condition here? So this is the basic variable having most negative solution. Okay, most negative solution means most negative bi, right? So this will be selected as the your leaving variable. So now once the leaving variable is selected, right, leaving variable is selected, the basic variable, the leaving variable is selected, we have to enter one variable. So the entering variable is now selected. The entering variable is now selected by using your optimality condition. Okay, so what is that optimality condition? So here the entering variable corresponds to the minimum ratio, right? It is a non-basic variable corresponding to the minimum ratio of what? Your solution row means net evaluation del j row divided by the leaving row, and here with strictly negative denominator, right? In previous simplex method we have strictly positive denominator. So while we divide, the denominator should be strictly negative, and the most negative variable here, that non-basic variable, will enter into your base. Okay, will enter into your base, and we continue the process to restore the identity matrix, for which we need the matrix elimination, Gauss-Jordan eliminations. Okay, so now if you compare these two methods, in your simplex method, initially the solution is feasible, means we have a non-negative solution, right? But it is not optimal. We move towards optimality, means we bring all del j positive for maximization problem. However, in dual simplex method, right, we have the initial solution is optimal, okay, optimal but not feasible. That means the solution may be negative, not feasible. We move towards feasibility. That means we achieve the right hand side is non-negative. Okay, so these are the basic things, but our concentration is at the cutting plane method, which use both simplex as well as the dual simplex method. So let me to explain what is a cut. Now let me to explain what is a cut. Okay, now talking about the chord, suppose we have a feasible region like this. Suppose we have a feasible region like this, right? This is my feasible region. If this feasible region, if this extreme points, this corner points giving a integer solution, it's fine. Integer solution, then it's okay. If not, we have to develop a chord. So that chord, this chord, suppose this is a chord, okay, this is suppose this is a chord, okay. I will tell you how to find a chord. Now this new feasible region, so these are my extreme points. With this new feasible region, whether we see that whether the integer solution is restored. If it's restored, then it's okay. If not, we again develop a chord. Okay. Suppose we again develop a chord. In that way, we continue till we get integral solution. Integer solution that may be mixed or all as asked. Okay. So this is the idea. What is the role of the chord? So what is a chord? So now what is chord? Suppose during solution we get a row. That 5 by 2 x1 plus 1 by 7 x2 minus 7 by 3 x3 is equal to suppose 5 by 2. Okay. So now how we develop a chord? Thus 5 by 2 we will write it. This is 2.5. So this we write it 2.5 means 2 plus half. Whole part plus fractional part x1 plus 1 by 7. Right. It is 0 plus 1 by 7. The whole part as well as fractional part. Minus 7 by 3. So minus 7 by 3, it is minus 2 point something. So the integral part here is next greatest integer is minus 3. So we will write it plus minus 3 plus 2 by 3 x3. Okay. Right. The next the greatest integer and plus the fractional part. And accordingly here 5 by 2 is 2 plus this is here equal to, it is here equal to 2 plus here half. Okay, this is the right hand side. So now we bring the whole part in left hand side. Okay, so that means it is my 2x1 plus 0x2 minus 3x3 and minus 2. We bring it in the left hand side and is equal to, here we bring the fractional part to the right hand side. It will be my, in right hand side we have here half, bring this to right hand side, minus half x1 minus 1 by 7 x2, then here minus 2 by 3 x3. Okay, since xi's are non-negative, here xi's are non-negative, so this must be smaller than here, this must be smaller than here half, this must be smaller than here half, is not it? So this must be smaller than here half, because it is half minus this is smaller than half. But you see here, the left hand side here is integer. As per the integer restrictions, xi is integer as per the integral restriction. So this is left hand side is an integer. Okay, integer. So the right hand side must be an integer. So this should be integer, is not it? So now this is a integral value which is less than half. Okay, so which is less than half. So the integer which is less than half, so the immediate closure integer is my 0. Should be an integer close to, okay, less than half, but close to, very close to half, or rather I can say the greatest integer of half. That means it is my 0. Okay, or I can say close to half means the greatest integer of half is my 0. Okay, so I write this as 0. Okay, so what is my chord now? So subsequently my cot is here half minus half x1 minus 1 by 7 x2 minus 2 by 3 x3. So this is my less than equal to here 0, right? So now if you simplify it, so this implies minus half x1 minus 1 by 7 x2 minus 2 by 3 x3, bringing this half to right hand side is less than equal to minus half. So this is a cot. Now this is a cot, okay, but the right hand side, so this is a cot. You see this right hand side, bi is negative here, right? So feasibility is lost, right? So feasibility is lost. Okay, we need to restore the feasibility. So this is what we introduce a cot. Feasibility being lost, we restore it by using the dual simplex method, and we continue the process. Okay, so let me solve one example. That means this is my cot. Okay, in that way a cot is developed. The cot is developed. A cot is developed out of this row, out of this constants. A cot is developed. So let us now solve one example. Now we are asked to solve the following IPP. Use cutting plan method to solve the following, to solve the IPP, right? So this is given all integer programming, all integers. Okay, if this is not given, then this is a LPP, as I have told you earlier. So here we need all integers. So now first we need to solve it by simplex method. Solution. We have the standard form. As I have told you, standard form. So we add a constant here. We add a slack variable here. It is 2x1. We first see the right hand side is non-negative. It's given. Otherwise we have to multiply negative sign to make it positive. It is 2x1 plus 4x2, and it is less than equal to 7. So we add a slack variable here. Suppose you add a slack variable here, x3. This is equal to my 7. So in second constants we have 5x1 plus 3x2, and we need a slack variable here. Since less than equal to, we add some non-negative value to make it balance, is 15. So what about my z? So my z is, my maximize z is equal to, here x1 is given plus 4x2 is given. So I write it here as 0x3 plus I write it here as 0x4. So you mark it. This coefficient is 1 here. You mark it. This is 0x3. Okay. So now you mark it. So this is here 0x4, and this is 1x4. So we find the identity column. You see 1 0, we are getting 1 0, we are getting 0 1. So this identity column we are getting. That means initially the slack variables x3 and x4 are the basic variables. Okay, and here x1, x2, x3, x4, these are greater than is equal to 0. So now we create the simplex table. We have the simplex table now. Simplex table. In simplex table, you see it carefully. We have the basic variable, then coefficient of the basic variable, then we have solution. I write it xb, and the variables as given x1, x2, x3, x4, and this will take part for the ratio, minimum ratio, to find a living variable. So now just we arrange as usual it is given. Okay, as usual it is given. So you see the x1 column here. So what are the basic variables? As I have told you, in the first row the basic variable is x3. In second row the basic variable is x4 here. So in x3, right? So now what is the objective coefficient here? CB is the objective coefficient. If I want to write the objective coefficient, the objective coefficient here is it is 1. The objective coefficient here is 1 here. This is 1. This is 4. So this is my 1. This is my 4. And this is my 0. And this is my 0. Okay. So the objective coefficient here is 0 and 0. So what is the solution here? the solution here is x3 is equal to 7 because non-basic variables are 0. At this stage, the basic variable are x3 and x4. Non-basic variable are x1 and x2. Non-basic variable are 0. So that means I am getting x3 is equal to my 7 and x4 is equal to my 15. That is my simply the right hand side. Okay. So now I just fill this row. It is my 2, 4, 1, 0 and it is my 5, 3, 0, 1. So you see here, this identity matrix we are getting. Is it not an identity matrix? Is it not an identity matrix? So you see this x3 being basic. So x3 and x3, the intersection point is 1. x4 and x4, you see the intersection point is 1. Okay. So now we have to see the what is my del j. We have to calculate some del j is cb into xb. That means this into this plus this into this. Okay. It is 0. And accordingly this and this here. It is 2 into 0, 2 into 0 plus 5 into 0 and this is my 0. Similarly all will 0 here. And my del j is my net evaluation, right? Del j is my net evaluation. It is called my net evaluation, right? It is zj minus cj. Zj minus cj. Cj is my objective coefficient. Is it not my cj? It is the coefficient here. Okay, I am taking the coefficient here 1 4 0 0 like that. Now zj minus cj, so it is minus 1. It is 0 minus 1 and it is 0 minus 4 minus 4. It is 0 minus 0. It is 0 minus 0. It is my minus 4. So you see the optimality is achieved when this all this del j, our intention is to search all del j greater than is equal to 0, then we stop. But here we have a most negative del j here, most negative del j here, right? So this need to be entered into the base. This need to be entered means x2 will enter into the base. X2 will come to this position. Okay, so once x2 will enter, one has to leave out from the base. So we have to find the ratio here. The ratio here is solution column means xb divided by here leaving entering row is x2 with strictly positive denominator. Means I have to find here 7 by 2. I have to find here 7 by 2. It is my 15 by 3. It is my 5. It is my 3.5. So this is minimum. So this is being minimum ratio. Okay, this x3 variable will leave from the base. So x3 is replaced by your x2. So in next set of solution, we have this is my x2 and we have this is my x4 is as usual. So you see, once this, the calculation must ensure that x2 and x2, this intersection point must be 1 and it must be 0, and this x4, it must be intersection point of x4 and x4, it must be your 1 raised to 0. So this need to be restored by using the Gauss-Jordan elimination. Okay, so for which we need the calculation. So now what is my objective coefficient of x2? The objective coefficient of x2 is 4 here. The objective coefficient of x4 is 0 here. I substitute it. Then I just have a calculation. Means I need to, this is my entering and this is my leaving. So this is my pivot position. This is my pivot position. This is my pivot position. Okay. So I need to bring this 1 and I need to bring this 0 as it is done here. Right. So how it is done? So we see this 4 need to make it 1. So this here R1 is need to be divided by 4. Means if I divide 4 here, it will be my 7 by 4. It will be my 2 by 4 means half, and it is 4 by 4 is 1. It is my 1 by 4 and it is my 0 by 4. Okay. So now using this 1, we have to bring this now 0. So originally it is 3 now. So this R2 is replaced by R2 minus 3 times this new R1. 3 times R1 new. Okay, because this is my new R1. This R1 is previous R1. Okay, So this is 3 times my new R1. So now using this 3 times 1, it is becomes 0. So I just have this calculation here. This calculation give me, so this calculation give me, it is my 39 by 4, and it is my 7 by 2, it is my 0, and actually it is my minus 3 by 4. Okay, so this is the calculations. With this calculation again I see what is my zj. Zj is cbxb, means this into this plus this into this, it is my 7. Then similarly we have this into this, it is 2. We have this is this into this plus this into this. Now second multiplication will not valid. It is 1 into 4, 4. It is 1 by 4 into 4 is 1. It is 0 into 4 plus this is 0. So now we calculate then here del j. Del j is zj minus cj. Means my, this is 2 minus 1. It is 2, 1. Then it is my 4 minus my 4. It is my 0. Then it is 1 minus 0. It is 0 minus 0. It is 1. So now you see here, we see here all del j, right? We see here all del j is greater than is equal to 0. So this is optimal. Optimality is achieved. So this is my optimal solution now. Okay. So in this optimal solutions, what I am getting, as all del j is greater than is equal to, at this stage the optimal solution is here x2 is 7 by 4, x2 is equal to 7 by 4, and x4 is equal to here, x4 is equal to 39 by 4. You see, this is the largest fraction here, isn't it? This is the largest fraction. So this row will be selected. We want to develop a chord here. Develop a chord with respect to this. Okay, with respect to this, and accordingly which are not here, means x1 and x3, these are all 0 because these are the non-basic variable. With z marks. What is my z marks here? My z marks is here 7. Okay, z marks is 7. Or if you substitute the value of x2 and x1 here, you see x2 and x1 here, if you substitute, then I am getting here x2 is 7 by 4, x2 is my 7 by 4, it is 0 plus 4 into 7 by 4 is my 7. So this, but this is not integral solution. Okay, so we have to develop a chord. Thus as 39 by 4 is the largest fraction, we select row 2 to develop a chord as follows. Now selecting my this row, it is 7 by 2 x1, 0 x2 minus 3 by 4 x3 plus 1 x4 is 39 by 4. So likewise we develop a chord. We write it 7 by 2 means 3 plus half x1, it is 0 plus 0 x2, and plus it is, we break it, we have the greatest integer here, it is minus 2 plus 1 by, it is minus 1 plus 1 by 4, minus 1 plus 1 by 4, it is added, it is minus 3 by 4 is x3 plus here 1 plus 0 x4, and this right hand side is 39 by 4 is 9 plus 3 by 4, it is 9 point something. Okay, so bring this to left hand side, here, and remaining to right hand side, and these are to right hand side. So this implies I am getting here 3x1 plus 0x2 minus x3 plus x4, and bring this to this side, minus 9 in right hand side. Here you have 3 by 4, bring this minus 1 by 2x1 minus 0x2 minus 1 by 4x3 minus 0x4. You see, since these are all negative, it must be smaller than equal to 3 by 4. What we need? A integer close to 3 by 4. It is 0 point something. The greatest integer is 0. So which is close to 0, as we need the integer. Okay, as we need the integer, because the left hand side is an integer here. It is an integer here. So the right hand side must be an integer. Okay, so this integer is 0. So we have a cut. So this implies my 3 by 4 minus a half x1 minus 1 by 4 x3 is my less than equal to 0. I bring this to right hand side. So this implies I am getting minus half x1 minus 1 by 4 x3 is less than is equal to minus 3 by 4. So this is a cut. I will introduce as a new constant. This is a new constant now. New constant, I add this new constant. Okay, and we have the new set of LPP as follows. So now we have, this is the cut. We add a slack variable since this is less than equal to. So this implies my minus half x1 minus 1 by 4 x3. We need a constant here, we slack variable x5. Okay, is equal to here minus 3 by 4. So now this is replaced by equal to sign with this add of this. This is my slack here, because already x3 and x4 are there. Okay, already x3 and x4 are there. Now we just take this solution. We just take this solution here, and we just write this as usual. We write this is the solution. Just I shift this table here, and I have this new constant is added here. New constant is x5 is added here. So with this new constant x5, so this will be my new constant x5. This x5 will be my basic variable here. So the coefficient of x5 will be 0 here because there is no z value here. So now this is my minus 3 by 4. The right hand side is minus 3 by 4. I write it minus 3 by 4, and as usual I write it is minus half x1. There is no x2. There is x3 is minus 1 by 4. There is no x4, and the x5 is 1. So this you see here x2, x4 and x5. x2 is 1 0 0. x4 is 0 1 0, means intersection of x4 and x4 is 1. Intersection of x5 and x5 is 1. This identity is always restored with the basic variables. Okay, so now you see now, so here the feasibility is hampered because this is the negative here. The solution is negative, means the feasibility is hampered. So that means this x5 will be my leaving variable by the feasibility conditions. We leave x5 from the base. Okay, if this x5 will leave from the base, we have to enter one variable. So what is my del j? Now I write my del j directly. I am writing del j is zj cbxb minus cj. Okay, so already since this is already 0, so this previous will work here. It will be same as here 1 0 1 0. It will same as 1 0 1 0 1 0 1 0, and for this final one also it is 0 plus 0 plus 0 minus 0. It is also 0. Okay, so now we need to find the ratio here. The ratio here is del j divided by the leaving row. Okay, this is my leaving row by x5 with strictly x5 is strictly negative. This thing we have to take this ratio. That means this means my here this by it is 1 divided by strictly negative minus half. This modulus of this will not take part. This will be my 1 divided by minus of 1 by 4 mod, because this is negative. This will not take part because it is positive, non-negative, and this will also not take part. So out of these two we have to find the minimum ratio. If you simplify it, it is here 2, right? It is equal to here 2 and it is equal to here 4. So this is minimum. So this is being minimum. So this will enter into the base. This x1 will enter into the base. So in next set of solution, here x1 will enter into your base, means x2, x4, your x5 is replaced by your x1. Okay, x1, and we continue the process. So you see now, since these are at the base, okay, these are at the base, so this x2 and x2, this intersection point, so this x1 and x1, this intersection point must be 1, this must be 0 and 0, and x2 and x2, this intersection point must be 1, x2 and x2, and this must be 0 and 0, and my x4 and x4, this intersection point must be 1, and this must be 0 and 0. In that way we have to apply the Gauss elimination. Now coming to this row first, we multiply, we make it 1 here, so here R3 is replaced by minus 2 R3. If I multiply minus 2, it is my 3 by 2, and it is my 1 0, and it is my, if I multiply here, if I multiply minus 2 here, it is here half, and it is here, so to make this possible, we use this to bring this 0, and we use this to bring this 0. So here R1 is replaced by R1 minus half R1. This R1 means now it is 1 here. Okay, now it is 1 here. 1 means it is new. And my R2 is replaced by R2 minus, it is already 1. So I multiply 7 by 2 here. 7 by 2 R1, it is new. After that my calculation will be, so now let me to fill this table, the coefficient of x2, x4 and x1. So coefficient of x2, x4 and x1, coefficient of x2 is given 4, x4 is 0, and x1 is 1. So now with these calculations it will give me 9 by 2, and this is my, this row will give me 0 minus 5 by 2, and this row will give me 1 7, and it is minus 2. Okay, so then I will calculate my zj. What is my zj now? My zj or del j directly I am calculating. So I am calculating here. What is my zj? Zj is cbxb. Zj is cbxb for the solution. So this into this plus this into this plus this into this, it is 4 plus 3 by 2 is 11 by 2. Now I am calculating del j. Del j is zj minus cj is cbxb minus cj, means this into this into this, plus this into this, plus this into this, minus here 0 here, minus here 1, minus this 1, 1400 is here, na? It is 14000 is here. So I am calculating it. So this will give me 0 0 half 0 2. You find all del j are positive here. You see all del j is greater than is equal to 0 here, right? At the same time you see this is also feasibility is already restored. Now this optimality is restored. So this is my optimal solution here. But however we have a caught again this is a max fraction here. This fraction is a max fraction. So with this row will be selected to develop another caught. Okay, here the optimal solution is at this stage the optimal solution is here x2 is equal to 1, x4 is equal to 9 by 2, x1 is equal to 3 by 2, and z is here 11 by 2. However it is not integer solution, thus we select row 2 to develop a caught as follows. So the caught here is minus 5 by 2 x3 plus x4 plus 7x5 is 9 by 2. So we have a caught. Okay, so this implies we just rewrite it. It is minus 3 plus half x3 plus 1 plus 1 x4 plus 7 plus 0 x5 is equal to 4 plus half here. Okay, so this implies we have minus 3x3 plus x4 plus x5, bring this 4 minus 4 in the right hand side, it is half minus half x3, bring this to right hand side, bring this to right hand side, minus x4, and it is 1 plus 0, 1 plus 0, so minus 0, it is 0, x4 is, there is no x4 here, so minus, so in the right hand side it is half minus, just to bring this to it is minus minus half x3, and this is 0 x4, no need, it is 0 x5, so which is smaller than your half, is not it, it is half minus something smaller than half, but the greatest integer is 0, which is close to 0 because the left hand side is an integer, so thus the cot is the cot is half minus half x3 is less than equal to 0, implies minus of half x3 is less than equal to your minus half. So this is the cot. Okay, this is the cot here. So we add a slack variable here, slack variable x6 we add, so we write it 0x1 plus 0x2 plus minus half x3 plus 0x4 plus 0x5 plus 1 into x6 is equal to minus half. Now we introduce it in this table, add this in the simplex table, simplex table. Okay, now we have the new simplex table is as follows. Now we just shift the previous table here, we just shift this table to here. Okay, and we have one more additional variable, that is my x6, that x6, and x6 is my 0 0 0, and x6 is here, and this is my 1, and this in this here only we have minus half x3, this is only minus half, and we have here 0, we have 0 0 and 0, and the right hand side is minus half. Okay, and the CB, the coefficient is x2 is 4, x4 is 0, x1 is 1, and here x6 is 0. So this is what we have the table. Now we see in this table the feasibility is hampered, because this is negative, the feasibility is hampered, so we have to first make it 1. Okay, we have to make it positive here, means here R4, R1 2 3 4, R4 is need to be replaced by here, we have to make it positive. No, actually this is the leaving row, so now we have to find a entering row. Okay, on this negative basis we have a leaving row, now we have the entering row. For that entering we have to first find here zj is cbxb, it is as usual here 11 by 2 as you get it. Now we have here del j is zj minus cj, cbxb minus cj, and we calculate it. This calculation will be same as the previous one here, 0 0 half 0 2 0 0 0, so it is here 0 0 half 0 2 0. Okay, now we have the ratio here is here zj divided by here x6 with x6 is strictly negative, we find the minimum ratio here, so this will not take part in the ratio, here only this will be half divided by, this is being negative, this is by minus half, this modulus, and this will not take part in the ratio, this will not take part because only negative denominator is this, so this is my minimum one. Okay, so this is my minimum, only this is the only one, and it is 1, it is your 1, and it is the minimum, so this will enter into the base. Okay, so this will enter into the base. Now this is the pivot position. Okay, this is the pivot position, so we need to make it 1 and we need to make it 0. To make it 1 we multiply minus 2 here, r4 is replaced by minus 2 times r4. Okay, minus 2 times r4, and in the subsequent table we have Here it is x2, x4, x1, and it is x6 is replaced by your x3. Okay, so this r4 is now need to be multiplied by minus 2 r4. So if I multiply it, it becomes my 1, it becomes my 0, 0, it becomes my 1, it becomes 0, it becomes 0, it becomes my minus 2. And since these are in the basic cell, the identity column is maintained here. So identity column is maintained. So x1 is having the identity column, so this must be x1, x1, and it is 0, 0. And x2 is having the identity column here, x2 and x2, it is 1, and it must be 0, 0. After calculation you must get it. Then here x4, this is x3, x3 is here. Okay, so this must be here 0, 0, 0, because x3 intersection is 1, and we have here x4, this must be intersection is 1, 0, 0. So this calculation will restore. Okay, so now we have the calculation here. So we need to make it 0, we need to make this 0, we need to make this 0. Okay, we need to make it, and we need to make it 1, so this calculation is there. Here r1 remains silent here, right? There will be no r1 remains silent, and here r2 is replaced by r2 minus 5 by 2 new r4, r2 minus 5 by 2 new r4. So during the calculation there is no calculation needed in r1, and in here r2 is replaced by r2, since it is here minus 5 by 2, so we add it, plus 5 by 2 r4 new. Okay, this is new. Then here r3 is replaced by r3, and it is here half, so minus half, we multiply half here, minus half times r4 new. Okay, means this, we are talking about this r4, and this calculation is like this, and this calculation is like this. If you multiply and do these calculations, it will give me 1, 7, 1 and 1, and the coefficient is as usual, it is 4, 0, 1, 0. This is as usual. So now we have this calculation will be, last two row we need 1, 7 minus 2, 1, 7 minus 2, 0, and it is 0, minus 5, 1, minus 2. Okay, with this we have now here zj is cb into xb. If you multiply it, this into this plus this into this, it is here 5, and here del j is cbxb minus cj. cbxb is my zj. Okay, so now if I calculate it, we are getting, or the cbxb throughout, let me to calculate it. It is here 1, this into this plus this into this plus this into this plus this into this, it is my 1. Accordingly this is my 4 here, and it is my 0, 0, 2, and this will be my 0 minus 5, it is 1, it is my 1, this into this only. Okay, now here this minus this coefficient here, we subtract cj here, and after subtraction it will my 0, 0, 0, 0, it is 2, it is 1. What we see, so this feasibility is already restored, right? No need to check it, we check it as all del j here, all del j is greater than or equal to 0, so optimality achieved. Okay, so we write the final solution here clearly. Hence the solution is optimal and feasible. It is already there, optimal and feasible. Also integrability is achieved. Consequently, the optimal integral solution is given by here x1 is 1, x2 is, sorry, x1 is 1, okay, x2 is also 1, right, x4 7 we don't need because these are in my basic is my x1 and x2 here. Or if I want to write in details, x1 is 1, x2 is 1, x3 is 1, x4 is 7, because these are all in base, x2 1, x4 7, x1 1, x3 1, and which are not there, these are all basic, basic variable. And non-basic variable is what? Non-basic variable which are not there in the base. x5 is equal to 0 is equal to x6 with z max is equal to here, right, here z is here what, x1 plus 4x2, yes or no, at the point 1 and 1, so this is 4 plus 1 5, also we get it here, so this is my final solutions, this is my final solution, this is the answer, okay. Hence the solution is because initially in the question we need only x1 is equal to 1, x2 is equal to 1 with z max is equal to 5, okay. This is the solutions as per the given question, because in the given question you have here x1 and x2, right, or you may write it, everything you may write, basic solutions, non-basic solutions, and optimal solutions with z max, with optimal z max, so we conclude. So to conclude the integral solutions, to conclude, the integer programming problem can be solved by two techniques, one in B and B technique, branch and bound technique, and other one is cutting plane technique. In branch and bound technique we use graphical or simplex, okay, graphical or simplex method, and then subsequently we have your inspection method, and we followed by the inspection method, okay, to get the solutions easily. But in cutting plane method we have to use the simplex method, and we find the highest fraction of bi, right, and you select it, develop a cut and solve as we did it, okay, and accordingly we continue this till we get all integers as, or the sum integers as it is being asked, okay. The problem is lengthy, so we have to see, you are to aware of the simplex method as well as the dual simplex method, because both the things are used here, simplex plus dual simplex is needed, okay. So you must go through the theory of both these things to have the awareness of solving problem. So the video is getting lengthy, we should conclude here. So now if this lecture is useful and interesting, please like and subscribe to this channel, which will boost my motivation to upload subsequent lectures for your benefits. So let us close the lecture here. Thank you all. Have a nice day.